Okay, good morning. It's a great pleasure to have Tomohiro Soejima as our speaker today. Tomo is currently a postdoc fellow at Harvard University, and before going to Harvard, he was a PhD student at Berkeley. And after this year, he will become an assistant professor at New York University. Tomo works on many topics, and I think one of the most distinctive styles of Tomo is to apply the state-of-the-art numerical approaches and also many interesting conceptual tools to understand very experimentally relevant topics. And in the study of these experimentally relevant topics, Tomo also obtains many further conceptually interesting results. I think today the topic is in this direction. We're all very excited to know about it. Thank you, Tomo.
All right, thank you, Eugene. I'm very excited to be at this seminar series. So today I'll be talking about something that's more on the analytical side of things, as far as things that I do go, which is a topological constraint on crystalline current. This is a paper that was posted a couple months ago. It's a work with Junkai Dong, Ophelia Sommer, Daniel Parker, and Ashwin Vishnuas. And I'll try to talk through starting from the very basics in section 1, and then gradually build up what exactly the problem is, what exactly needs to be computed. But just to give you a flavor of what is to be done, what we are imagining is some kind of two-dimensional system of electrons, where electron interaction forces the electrons into some crystalline insulating state. Most famously, Wigner crystal gives you such state. And then we make it move. Maybe we add some external potential, or maybe we add some heat so that some quantum modes get excited. And then these crystals start moving at velocity v. The question I want to ask is, what's the current when I have this crystal that's moving at velocity v? A classical intuition tells us that this current should be proportional to just the charge of electron, the density of the electron density, and then the velocity of the crystal. I'll tell you, however, that this intuition is in general incorrect, that there's an additional term that you need to keep track of that determines the actual microscopic current that's being carried by a crystal that moves at velocity v. So that will be the final goal of this talk. If you are convinced that this formula is incorrect, then I will have done half of the job. Okay, so to set it up, though, I want to take a step back and carefully think about what kind of classification of phases of matter we need to apply in this problem. So to do that, I'll think about Witten-Strata formula. So I'll again draw a two-dimensional electron gas, but it's crystallized. And it's crystallized into an insulator, so we have sigma xx equals 0, and then sigma xy in general is equal to c e squared over h, where c is the many-body Chern number. Now let's take this two-dimensional gas and then imagine adding some B field to the system. Additional B field in the case where if we started from some B field. Then this generates an electromotive force that goes around. And the electromotive force, in turn, draws or pushes electrons away according to the Hall coefficient of the insulator. The net result is that if you look at the electron density as a function of the B field at the fixed chemical potential, so that the density is allowed to change, then this will be given by sigma xy, which is in turn proportional to C. This is the content of the Witten-Strata formula. And so from this, we can get rho is equal to sigma xy, or I will write it as C. Rho is equal to C phi plus, and the leftover part, which is S over AUC. But AUC is the the area of the unit cell of the crystal. And this is something you can detect and measure in experiment. What you typically do is to make a plot of the electron density rho and the magnetic flux density phi. So this is flux density. And you plot where you see an insulating state, because an insulating state means that you're keeping the chemical potential to be fixed. If you have a vertical line that corresponds to C equals 0, if you see a line that's sloped, it means that there's non-zero C, such as 1. You can also see things that show up from either zero density or maybe at finite density, depending on what kind of state you have. And importantly, once you identify each of the slope, you can map that back to the formula. So really, each state is characterized by the pair C and then S over AUC. Okay. So using this, we can classify states. And for later convenience, let me actually draw the rho phi over here. Okay, so we have the C S over AUC pair to keep track of. So let me make a 4x4 table. That looks at the value of C and then value of S. So whether C is 0, C is not equal to 0, S is 0, S is not equal to 0. Let me start from the top right corner. This is satisfied by a Wigner crystal because it has non-zero density, but it has zero Chan number. So this is a vertical line over here, which is a Wigner crystalline state. On the bottom right corner, I have a state that with non-zero Chan number. This has been termed partial Hall crystal. By Axel Tesanovich and Halperin in 1980s. And this corresponds to these sloped lines that has a finite x-intercept. And finally, on the bottom left, we have what's called full Hall crystal. And these corresponds to lines that emanate out from origin. So these states are the full Hall crystals. Why did I skip the top left corner? Well, S is 0, C equals 0. So over here, there's no electron density, so I'm going to ignore this possibility. So this gives us 3 different kinds of crystals. We see examples of them.
Sorry.
First of all, yes.
Here S is defined on top of some valence electrons, or is it the total electron?
Yeah, so you need to start with a model that only keeps track of the mobile electrons, right? So if, for example, if you have a semiconductor and if you're doping into it, you're only keeping track of the conducting electrons. And the classification is only as good as your approximation. If there are other electrons that might be in the system, then, well, okay, once you fix the reference, the classification is still good. But maybe the value of S itself might not actually have an invariant meaning.
Yeah, and then here when you say S over AUC, do you mean the fractional part or the total number?
So typically S over AUC is an integer. Sorry, S is an integer. Because S is the number of electrons per unit cell. So, but S could be fractional, but in that case, you have a fractional state usually.
So then, in this partial Hall crystal, what is the example of S over AUC in that case?
I'll give you an example partial Hall crystal, and then I can come back to that question.
Yeah.
Okay. Any other question? All right, good. So I'll give you some examples. In the case of regular crystal, this is simply going to be a regular crystal. This is a trivial example of the phase, the namesake of the phase. So I don't have that too much to say about that. Let's look at the partial whole crystal though. This needs to be a state that has a finite Chern number but is also crystalline. And the prototypal example of this can be prepared by starting from lambda levels. Let's say we have some lambda levels. And then we start by filling the lowest lambda level, fully filled lowest lambda level, in fact. Then this state has C equals 1. Now let's dope holes into it. So we'll remove some electrons. And we will let these holes crystallize. If these holes just form a standard Wigner crystal, the end result is still a C equal 1 state. But now the density has deviated from the original value. How much has it deviated? Let's say we've added some epsilon electron over here. Then if we go back to the top left, let's say this line was the line that corresponded to C equal 1. Then that's where we started from before we started doping the system. Then by doping it, I am now at over here. There's an epsilon difference between them, right? So if I want to compute F over AUC, what I need to do is to extend this line with the same slope and then look at the intercept here. So in this case, what we'll find is that F over AUC is equal to minus the absolute value of epsilon. So F is given by the amount of doping you did relative to a fully filled lambda level in this example. Liu-Jun, did this answer your question?
Yes, thanks.
Great. Now this is an example that happens at finite D field, or at least it's built at finite D field. There are more recent examples of this kind called anomalous hole crystal. This is a state which has non-zero Chern number at 0B field owing to spontaneous time reversal symmetry. Then that you can think of as the zero field limit of partial whole crystal. Sorry, this is supposed to be PHC, not PWC. These anomalous whole crystalline states have been conjectured to exist in rhombohedral pentalayer graphene under certain conditions, which was actually the original reason why I am interested in the problem of topological crystals.
Tomo, you said
And
it's
finally,
conjectured to
yes.
be. You said it's conjectured to be, so you think there's some doubt?
Well, at the mean field level, I don't have much doubt that there's some part of the phase diagram that has anomalous whole crystal. Experimentally, there's no direct evidence of anomalous whole crystal. So I would say it's still a conjecture. It's a well-motivated conjecture theoretically, but if you just look at the experimental data, without theory input, it doesn't scream anomalous whole crystal or anything.
So experimentally, there is a quantum Hall effect, and
Right.
but the question is whether it's a crystal.
Right. And in fact, if you remove Morin potential and then look at the phase diagram, people get superconductivity or metal instead. So in the naive, simplest setup people have looked at, they actually get luckier in the sense like superconductivity is probably more exciting. So you get chiral, possibly topological superconductor instead of a normal full crystal.
I see. If I remove the Mori potential.
Right.
Experimentally, what does it
So
mean? What does it mean to remove the Morley?
experimentally,
Mhm.
what it means is that the Morley potential comes from the hexagonal boron nitride, right?
Uh-huh.
And the period of the Morley potential is controlled by the alignment between HBN and
Uh-huh.
graphene.
I
And
see.
when the alignment is bad, then like the frequency of the Morley potential becomes very high. So you can average it out and ignore the effect of the Morley potential.
Mhm.
So in the regime where the alignment is not present, we call it more or less, even though technically there's a very high frequency Morley that's doing the
Okay.
system.
Thanks.
Great. Okay. Well, for full hole crystal, what we can do is we can again start from the lowest Landau level, fully filled lowest Landau level, and now we can create particle hole pairs. So actually, let me add 4 electrons here. To create particle hole pairs, you can just excite some of the electrons into the first Landau level instead of the 0th Landau level. So now there are some electrons here, and these are extons, which simply means a particle hole pair. And if you crystallize these extons, then that gives us a full hole crystal, since the exton crystallization can give rise to real space charge density variation. Importantly, if you have a full hole crystal, the object that crystallizes at least in this particular example, is an exton, which is a neutral object, even though the system consists solely of electrons. And this fact will come back and explain some of the peculiar features we will see of the full hole crystal. Okay, any question up to this point? If not, let me move on to the second part. So in the second part, what I'll do is to define a sliding crystal microscopically and carefully. It turns out if you try to do things microscopically or by intuition, there are many ways you can fail. So even though it might appear a little technical, I want to guide you through the exact process of defining a sliding crystal and why that is necessary to get the physically correct answer. So to start, I need to define my Hilbert space. So my Hilbert space will be that of electrons on a torus. And there are 8 electrons on the torus, and I will let it be pierced by magnetic field that's perpendicular to the plane. The total flux value of this I'll set to be n of phi. In addition, when you have a torus, you can set the boundary condition of the system. So I will set this to be, I'll set 2 boundary conditions, phi 1 and phi 2. How is this determined? It is determined by translation around of a single particle wave function. So the TLI is the single translation operator along each length of the torus. This transforms state as e to the I by I psi. When psi satisfies this condition, we say psi is in the Hilbert space that's labeled by the flux sector phi, for which I will use this vector notation.
Tomo,
So this is my,
is this translation or magnetic translation?
It's magnetic translation. So they follow the magnetic translation algebra. Yeah, thanks for the clarification.
Yeah, so this T is the magnetic translation, not the translation, right?
Yep. So
Mhm.
it also does the change in the of the gauge or change of the, it keeps track of the vector potential, ensures that you're going back to the same vector potential configuration.
Yeah, thanks.
Okay. Now, as Division was pointing out, because we have magnetic field, we have magnetic translation. So this actually was a magnetic translation. And these magnetic translations satisfy the magnetic translation algebra, which is e to the I, e b, u wedge v, tv to u, where u wedge v is ux dy minus uy dx. Okay, so that's the Hilbert space. Now, there's one very important thing to note for later, which is the action of the translation of the Hilbert space. So let's start with some psi, which lives in a particular Hilbert space. Then what we can do is to act with t hat u. Now, what's the boundary condition of this? To see it, I can act with TL, let's say 1. And I need to commute them past each other. So I get tu hat TL1 psi, and then e to the I EB L wedge U1, which is then equal to e to the I EB L wedge L1 wedge U e to the I phi tu psi. So from this, we see that tu psi actually now lives in a different Hilbert space with some delta of phi. And the delta of phi is given by EB Lx Uy minus Ly Ux. So the magnetic translation symmetry is not actually a unitary. It is an isometry that maps you between the original Hilbert space to another Hilbert space that corresponds to a different boundary condition.
Tomo, again, just to make sure, are you assuming here n phi is an integer multiple of the flux quantum?
Yeah, and phi is the number of magnetic flux quantum.
And it's an integer multiple, right?
It's an integer because of the Dirac monopole quantization condition.
Yeah.
Great. Okay, so this is a Hilbert space. I will come back to this several times during the rest of the talk. And in this space, now we need to define our Hamiltonian. Our Hamiltonian, we'll write it as H equal some kinetic part plus some interaction part. And they are all symmetric under magnetic translation symmetry. Okay, so how do I define a crystal in this case? We need to follow a standard procedure of adding a pinning potential. So what we'll do is to start with the symmetric Hamiltonian. And add a perturbation. The perturbation has strength lambda, and it has spatial dependence. And the spatial dependence I'll denote by the vector u. So this Hamiltonian is parameterized by u. Now, why do I do this? Well, this is so that I can choose one of the states out of the manifold of ground states or low energy states that forms when you have a spontaneous symmetry breaking. So, for example, if I want to compute an order parameter, what I do is first, from this Hamiltonian, get the ground state, which I'll label as u lambda, and then the system size L. And then any order parameter I can compute by computing the expectation value at finite lambda and L and U And then first take the limit of L going to infinity, and then take the limit of lambda going to 0. This is the typical procedure to detect symmetry breaking in quantum systems. So what we want to do is to measure compute current. So we need to take a similar kind of limit, except current will not be an instantaneous property of the ground state of the system, since in the ground state, because of Bloch's theorem, there's no current flowing that's persistent. So instead, we need to plug in some formula for current over here. And then we can take the same order of limits, and then we can compute the crystalline current in the infinite system size limits. Okay, so what should this formula be? To think about it, let's think what is a natural definition of a sliding crystal. Well, if I have h of u, then at each value of u, the instantaneous ground state is at location u. Like its location is shifted by the vector u relative to when that value was 0. So we already know that this gives me a state that's labeled by u, lambda, and then L. So what I can do is I can make the u be time dependent. And if I make this u of t vary slowly enough, then from adiabatic theorem, we know what that will give me. What it will give me is just simultaneous ground states all the way through. So I'm moving this, when I add this spinning potential and move it slowly, the time evolution was simply given by a movement in this manifold of low energy symmetry broken states. So what I'll do is I'll define this to be my phi of t, and then I'll compute the current associated with this phi of t. And the way of computing current in this setup is well known. We use what's called many-body polarization. So this is given by Tx is equal to Lx over 2 pi im log phi of t e to the I 2 pi over Lx x hat psi t. And then we can compute the current by the time derivative of this object. And if you haven't seen this, this many-body polarization is defined to make sure that the quantity is periodic and x goes to x plus Lx. Since otherwise you need to deal with discontinuity that happens at the edge of the system as you go around the torus. Okay, so now we have two ingredients. The first ingredient is my state psi, and then the second ingredient is the formula for computing current, so I can just put them together. When doing so, we'll notice the following. So first, let me just set psi at t equals 0 to be just u at t equals 0. And I'll drop lambda and L since they will be taken to either infinity or 0 later on, but we can just keep them fixed for now. But let me start keeping track of the flux sector I am in. I am in the flux sector which is finite. Now then let's ask what the state psi of t is. Well, the state psi of t is u of t, and it's still in the same flux sector because it's being time evolved within the same Hilbert space. So now I can write this as t of u and a state that's at the origin. So we are using action of magnetic translation to transport the location of the crystal back to where it started from. and I'm setting that origin to be location 0. However, this comes at a cost. What this does is actually it changes the flux vector in a time-dependent way. And then this delta of phi t is given by EB Lx uyt L minus Ly uxt. Okay, so is this how can we compute the current? Well, there's a fast component which comes from acting with TUT inverse e to the I 2 pi over Lx x hat TUT. These are magnetic translations, but the actual magnetic translation position is straightforward. It just shifts the position. So what this does is it simply turns it into e to the I 2 pi over Lx and e times ux of t, and then e to the I 2 pi over Lx x hat. So the magnetic translation part, just goes through, gives you a constant prefactor, well, constant factors that will then contribute to current. But then there's a remainder part that's interesting, right? The remainder part is 0, phi plus del phi t, and then e to the I 2 pi over Lx, except 0, phi plus del phi t. What is this part doing? This part is looking at the contribution to current from changing flux. Now, what's changing flux? Changing flux is nothing but an electromotive force. So what this is capturing is that this is actually capturing a contribution from Hall conductivity. So the Hall conductivity contributes to current. If you put these two contributions together, what you get is that J is equal to E, and then there's a fast contribution which is proportional to electron density since it's rho. And then there's a second contribution which is proportional to Hall conductivity as well as the strength of the B field, so the flux density. So they combine to give us J is equal to E rho minus C phi B. If we go back to the strata formula, this is also equivalent to E times S over AUC times D. So this is the main result of the paper. The current carried by a crystal picks up a topological correction, which is proportional to the Chern number and also the flux present in the system. Since this is important, I want to stop here for if there's any question.
I have a question. In deriving this
Yes.
result, is it important to assume that the interactions are density-density interactions?
No, it just needs to be translation invariant. I do not need to assume it is density-density, even though I wrote it as such in defining the Hamiltonian.
Mm-hmm. The important part there is that the position operator on the magnetic translation is the same as on the usual translation.
The position operator in many body, yeah, it only really cares about the algebra between many body polarization and magnetic translation. So as long as, in fact, it doesn't need to even be just a two-body operator, right? It could be like many body interaction as long as it's local and it satisfies most of the state stability of matter conditions, and my proof will still go through as long as magnetic translation is still present.
Mm-hmm.
I guess the only tricky thing is if it's something like correlated hopping, then it needs to, you need to make sure that the phases transform correctly under the actual magnetic translation such that it's still symmetric. But that's a technical point, not like a physics point, really. It's as long as you prepare such correlated hoppings, then the proof will go through.
As long as, sorry, for correlated hopping, as long as I do what, then it will go through.
Well, you just need to make sure that the hopping part couples to the gauge field correctly, so that when you do magnetic translation on it, it transforms correctly.
Mm-hmm.
So it needs to look like, if I go back here, a correlated hopping term, the naivest one just couples density to some kinetic energy, right? And then like the kinetic energy part needs to take in the same vector potential as the actual kinetic part. But this is straightforward to implement.
Yeah, I see. Thanks.
Okay. Any other question?
Yeah, maybe I can ask a potentially stupid question.
Mhm.
So in this
Oh, no stupid
computation,
question.
in this computation of
No,
this,
I mean, yeah.
yeah, in this computation of the whole conductivity, it's with respect to the shifted phi, right? So
Mhm.
I'm just trying to see like how. So if I understood correctly, this small phi that you defined, that's the flux quantum in the system. But how come like
Okay,
yeah,
maybe my notation was a bit confusing. So the two places where phi shows up, there's like this one over here, right, and
yeah,
this over here.
yeah.
Uh, and then there's also like lowercase phi, which is like used for flux density.
Okay.
So in the derivation here, I am always dealing with the boundary condition setting phi, like the thing that sets how much phase you pick up after you travel. This is different from the lowercase phi, which is proportional to the strength of the B field.
Mhm. Okay, okay, I see. So if I pick you, so this, right, so sorry. Let's say I pick this U vector to travel around one single unit cell, and this phi would pick up additional contribution, which you have this new
Mhm.
flux that's living inside this unit cell, right? Or is that
I
the right
think
way to understand
I was cut off
TNS1
for a
or?
bit.
Okay.
Yeah,
So
so
what I was
sorry, I think Zoom cut off for me for a bit.
okay. So I'll repeat the question.
Thank you,
So
thank you.
yeah, if I pick this U vector, it's parameterized by T, and then
Mhm.
if I make this parameterization to just go around the unit cell, like one single unit cell,
Mhm.
then this phi would be, it'll just pick up like one additional flux density over that unit cell, right? Like it would just have that additional contribution. Is that the right way to think about this, or?
So yeah, I think you're thinking about the Aharonov bond phase you would
Right.
pick up as the crystal goes around, right?
Yeah.
It is very closely connected. The contribution here will be proportional to Aharonov Bohm effect. In fact, I'll talk about it in the later section, section 4. So maybe
Okay.
I can describe it in more detail in that section, like what the
Okay.
exact connection is.
Okay. Great. Thank you.
Great. Thank you for the question. By the way, sorry, when I said no stupid question, I meant there is no stupid question, not that I will not take stupid questions. So please feel free to ask any question you may. Oops. Give me a second. Okay. Any other question? If not, I'll give you some examples and then a mnemonic that you can take home with you to remember why this formula is actually the only natural thing that can happen. It's a strong claim, but I'll back the strong claim out. Okay, so let me start by examples. So first of all, we already saw that J is always ES over AUCV. So what this is saying is that this S, which is sometimes called bound charge invariant, is the only thing that carries charge. Like only the bound charge, quote unquote, moves around when you move the crystal. So it tells you that the main bound charge is actually a very, very apt one, because that's the only thing that gets dragged around if you shift the lattice. So that's more of a remark than an example. Now let's start actual examples one by one. First, let's do Wigner crystal. Well, Wigner crystal has C equals 0 by definition, so the correction term is trivial. And for later use, let me just put the formula for J up there. So this means that J is E rho V. So this matches our classical intuition. Our classical intuition is exactly right. Okay, now let's think about Wigner crystal of holes in the lowest Landau level. And you already kind of know what happens, but I actually want to give you a nice way of thinking about this and constraining the behavior. Let's start from a Wigner crystal of electrons in the lowest Landau level. In that system, let's say I have some charge density rho. Char number is 0. And then J is simply E rho V. Now, in the lowest Landau level, what I can do is I can perform a particle hole transformation. So now I have holes and then field electrons. When you do that, you get first, the density will change to phi minus rho, because phi is the field Landau level and we've removed rho electrons from it. C will be 1, because we start from field Landau level. And then J is now going to be E times phi minus rho minus C, which is 1, times phi. So the phi's cancel each other, and then we see that this is minus E rho V. So indeed, it transforms correctly under particle hole. Instead of having a positive current, you actually have a negative current, which is actually interesting. There's only electrons in the system, but it is allowed to carry current that's opposite of the electron charge, because you're starting from a reference that does not carry any current with it. Another intuitive example is to consider a fitting fraction, mu, which is rho over phi, that is very large, let's say like 50.3 or something. Then if you think about what kind of state you might get, the natural state to write down is to fill 50 Landau levels and then just add 0.3 electrons in the top Landau level. Now, a standard way to deal with this problem is to freeze these 50 Landau levels and only look at the dynamics of electrons in the top Landau level. So our intuition tells us that J should probably be 0.3 phi EV. And now we can check this using a formula. So if you use our formula, J is equal to, first of all, I'll rewrite it in a form that's nice. So I can write it as E phi nu minus C V. The nu is 50.3. Because I have a field Landau level, C is 50. So this is indeed 0.3 E phi D. So our result confirms our intuition that comes from freezing of the Landau tables. But importantly, this result over here, this is fully robust. Even if you undo the freezing assumption, the value of the current doesn't change because it only depends on the many-body invariant, which does not depend on if you are keeping the approximation or not. So as long as you have a state that has Chern number 50, no matter how many particle hole excitations you may have, it still carries the same amount of current. And finally, if you have a full hole crystal, then it has S equals 0, which means that J is actually 0. So even though it's a crystal with a charge density variation, when it moves, it does not carry any current. And this is one simple way to understand it is to think of this as a crystal of extons, which has positive and negative charge, and they move together with the same velocity. They cancel each other out, so even though there's charge density variation that's moving, it does not carry any current with it. Any question about these examples? If not, I'll give you a quick argument from Galilean invariance that fixes the shape of the formula. So how do we do this? Let me first start with a collection of electrons, let me apply some electric field. E is equal to minus velocity times v. And when I do this, it induces current because there's a Hall response. So the Hall response is going to be J is equal to sigma times E, which if you work it out becomes C times phi times V. This is just because of how I set my E field to be proportional to V and B. Now let's do Galilean boost by velocity V. So what do I get after this transformation? I get V. The E field is now 0 because I set my original E field to precisely be cancelled by the Galilean transformation. Now there's some current J, but what's this current? This is equal to the original contribution, which was minus C phi V, and now a contribution from Galilean boost, which is proportional to rho. So the other way of looking at what's happening in the system is to decompose it. First term is E rho V. The second term is coming from the Hall response. The first term Galilean invariance, the second term coming from the Hall response of the system. So this is why this formula is very, very natural. In the presence of Galilean invariance, just knowing the macroscopic response of the system entirely fixes what this formula can be. Okay. Any question? Let's see. In interest of time, I'll be slightly quicker in the rest of the sections. But since I've already shown you the main result, the rest is going to be relatively straightforward. So in part 3, what I'll show you is what's called anomalous dispersion. And the idea is that if you have a phonon action, and it's going to be decomposed into 2 parts. There's a center of mass part you can write down, which is simply going to be an E and then n over 2 U dot squared plus beta over 2 U cross U dot. And then there's going to be a kinetic. This needs to be integrated. And then there's going to be the elastic energy part, which is some lambda A, B, C, D, del A, UB, del C, UD. And because I'm interested in sliding crystal, I will only keep the center of mass part. And if I keep the center of mass part and then solve for the equation of motion, I'll find that it generates mu dot dot is equal to beta u dot cross z. This is simply a low-length force. Beta is the coefficient of the low-length force that the center of mass feels. Now, up to this point, beta is just some random number. But in a system that we're considering, we know the origin of low-length force. It will be the actual microscopic low-length force that is coming from the presence of the magnetic field. So we can match this with the actual low-length force, which is going to look like rho inverse J times B. And then we know how to write J. It is E over rho minus C phi, and U dot. And then B is in the Z direction. So that gives me Z. So the end result is that this beta term, which tells you the strength of the low-length force, is actually completely fixed by the previous calculation we've already done. It's EB1 minus C phi over rho, or to write slightly differently, it's SEB over rho times AUC.
A question, why is it U dot in the last step?
In the last step.
Yeah.
So J is E rho minus C phi B, and then B is U dot.
Oh, I see. U is the coordinate V, that is V.
Right.
This is telling us
Thank you
in
for the
this
question.
kind of anomalous Hall crystal, there will automatically be a term in the phonon action with the specific coefficient.
Exactly. Whenever you have a topological crystal, this term is completely fixed by the charge density and the topology and the magnetic flux of the system. And we have seen this term before in where if C was 0, then this is just telling us that beta is equal to E times B, right? This is the usual electromagnetic coupling between electrons and the magnetic field in a Wigner crystal. But again, we are picking up this topological correction that was not obvious unless we went through the quantum mechanical derivation. Okay, so this has an interesting consequence. If you work out the dispersion relation of a phonon, when beta is equal to 0, you can find that genetically you have two gapless modes corresponding to transversal Goldstone mode and then longitudinal Goldstone mode. When beta is not equal to 0, on the other hand, you gap it out. One of the mode remains gapless, but then the other mode actually becomes gapped. And this is because the transversal motion and the longitudinal motion now gets coupled, right? Now the sliding crystal starts rotating because of the low-length force. And we knew this from before in the context of Wigner crystal. At 0 B field, the left-hand side is what happens. But if you add B field, then the right-hand side happens. And the same thing goes for partial Hall crystal, since partial Hall crystal, as long as it is at non-zero B field. If I have an anomalous Hall crystal though, which by definition needs to be at 0 B field, then the scenario on the left-hand side will happen. What's interesting though is the last possibility, which is a full Hall crystal. for full hole crystal, even though that is potentially a very strong magnetic field, what happens is the scenario on the left-hand side. So it breaks this pattern. And the reason why it breaks this pattern is that beta is proportional to both B and S. So you can make S go to 0 to realize the left-hand side scenario instead of making B go to 0. So crystal in the magnetic field that still manages to behave as though it doesn't feel any Lorentz force. When I first saw this, I was quite surprised. This was this result for specific model was computed by Axel Tesanovic and Bart Halperin, but I didn't understand why this could be the case. But now we understand why this is the case. This is because J is equal to 0. And when J is 0, of course, there's no Lorentz force that can act on the crystal since it doesn't couple to the B field. And this in turn comes from the fact that the state could be understood as a crystal of exons. So at least for me, it resolved this tension between a previously existing calculation in the literature that told me that there is this weird full hole crystal scenario in which the dispersion can ignore the B field. And then the fact that there's still some B field in the system. This is resolved by just observing the current is 0 in the system. Any question about this?
No question, just a comment. This is very nice.
Yeah. Oh, thank you so much. Thank you so much. Let's see. If I can go over by 10 minutes, I can probably briefly talk about anomaly matching. Would that be all right?
Sure, go ahead.
Okay. So now let me switch gears from dynamics a little bit and then tell you about the Berry phase. So this goes back to one of the questions from earlier. Instead of thinking about the crystal that just travels in a straight line, we'll consider a loop. Now, I can compute what happens in this scenario from just the center of mass action, right? What I'll do is I'll just quantize the theory by putting the action on the exponent of an exponential and then try to compute what this phase is. And if you work this out, what you end up getting is a contribution that's proportional to the number of electrons, the area of the loop, which I'll call as A, and then beta. So this is a prediction for the quantized theory of the center of mass of the crystal. And this needs to be matched by the microscopic theory. And in the microscopic theory, we can compute the Berry phase, rho beta, by integrating the imaginary part of u of t and then del of t, e of t, right? This is the Berry phase of an object that goes around the loop. And just as we picked up a topological contribution when u of t was moving along with the pinning potential, here again we are keeping track of the time relation, so the same contribution shows up. So if we work this out, then we find that this contribution is indeed NE times E times the B field times 1 minus C times phi over rho times A. So from this, we can also fix that beta is equal to EB 1 minus C phi over rho. So this is a more microscopic definition and derivation of what beta is. which doesn't rely on, for example, the fact that the coupling between electrons and the magnetic field takes exactly the form, the Lorentz force form. Okay, so this is the Berry phase. Now it's relatively short, but why did I bother to quantize the theory? This is because I actually wanted to perform what's called anomaly matching. So what's anomaly matching? There are many variants, but the one I'm interested in is in matching the two theories that I have. So on one hand, I have a theory of electrons, right? I have degrees of freedom, a bunch of C delta C's, right? And then I have my set of ground states, U of, and I'm interested in how this system behaves and the action of translation, for example. So I have a set of operators, magnetic translation operators, which I'll write as TU, UV, because this is a microscopic theory. On the other hand, I have this theory that's described by the center mass action, which is simply NE and then M over 2 E dot squared plus beta over 2 E cross E dot. And then the degrees of freedom here are just described by a single vector U, which could be time dependent, right? And it also has a translation action that you can derive, which I will call as IR translation. So the statement of anomaly matching is simply that the algebra of these translations must match each other. Okay, so specifically, what do I mean? Since we have magnetic translations, the best thing to do is to consider the following commutator, which is TU of UV, TV of UV, and then T minus U UV, T minus D UV. This should equal TU IR, TV IR, T minus U IR, T minus D IR. So this is our anomaly matching condition. Now, let me do first what I will call naive matching. I call it naive, but this is precisely what I did when I was initially thinking about this problem, and it didn't give me the right answer, and it was driving me crazy. So let me first give you which mistake I made. So it is tempting to set U and V to be the infinitesimal versions, right? Because I can just make these translations to be as small as I would like. So if I do this naive matching, then what I'll find is that the left-hand side is e to the I EB, and then something that scales with epsilon squared, and then the number of electrons NE, and then the area that's spanned by UHV. And then on the right-hand side, what we will get is that this is equal to e to the I beta, and then epsilon squared NE, and again, something that scales that goes as UHV. From this, I can just take epsilon to 0, and then the left-hand side and right-hand side need to match. So I can conclude that beta is equal to EB. But we know this is wrong, right? We are missing a contribution. We are missing a topological contribution. Somehow this naive matching procedure does not give us the correct answer. So why is this wrong? And actually, I already showed you why this could be wrong. So what's the correct matching procedure? Correct matching is given by noticing that if I start with some psi in the Hilbert space, then translating by U gives me in a different Hilbert space in general. So the infinitesimal translations are not actually a symmetry of the microscopic UV problem. In terms of symmetry, what this means is that what we might have thought as a system with continuous translation symmetry actually only admits discrete translation symmetries. That the order of the discrete translation is actually given precisely by the number of magnetic flux quantum in the system. So now there is some minimal translation I can do, which is still on unitary, not just on isometry. Let me call the generator of that B1 and B2. Then the anomaly that needs to be matched is B1 UV, B2 UV, minus B1 UV, minus B2 UV equals T B1 IR, B2 IR, minus B1 IR, minus B2 IR. Good. So now left-hand side, what will that look like? I'll skip the algebra, but once you work this out, you find that this is equal to e to the I 2 pi times rho over phi, or equivalently, I can write it as e to the I 2 pi nu, where nu is the fitting factor of the lambda levels. On the right-hand side, on the other hand, what we get is e to the I 2 pi, and then beta over EB beta over EB, I think. Okay, so now I need to match these objects. And actually, I think I need a row over here, but not this. I'll fix later. I need to match these two parts, right? So what we need is beta over EB. Phi to be equal to nu mod 1, right? So this in turn actually gives us a condition. I'm now realizing I messed up a factor. I apologize. This should be phi over here, and then this should be phi over here. This gives us a condition that beta is equal to EB phi, and then nu minus m over rho. So this is a constraint we get from anomaly matching. Compare this against the actual result we have. The actual result we have is beta is equal to EB phi over rho nu minus c. So we see that the ambiguity that's left open by this anomaly matching procedure is precisely the one that's captured by the many-body Chern number. So the many-body Chern number is telling you how to lift the translation, the microscopic translation that's discrete, to the continuous translations. And there are many different ways of doing it. There are actually infinitely many ways of doing it, and each individual one is captured by the many-body Chern number of the system. So I'll just summarize what we found. We started from the rhythm strata formula, rho equals C phi plus S over AUC. And we found that the current is given by E rho minus C phi V. We saw that how that can be used to constrain the Berry phase term, which is e to the b phi over rho mu minus c. And finally, by doing anomaly matching procedure, we actually realized that this was almost preordained in the sense that the matching already gave us that this condition must be satisfied. Okay, there's some generalization to fractional parts and then generalization to fermions I could talk about, but I think this is a good point to officially and start taking questions. Thank you so much for your attention.
Thank you very much for the very interesting talk. And let me ask you a question. So,
Yeah.
here, C is an integer because is this connected to the assumption that the action S is simply written as some function of the coordinate U instead of some additional dynamical parts?
So you're wondering like why is it integer not like why does it not allow fractional value? Right. That's probably your question, like the motivation behind your question.
Yeah.
And that's the part I skipped. The reason why this only tells us integer case is that in general, when you take your UV translation operator, let's say UV, and then map that to try to map that to translation in IR, for non-fractional state, like it just has a one-to-one mapping between like UV to IR because this is the only low energy degree of freedom that's present, right? The location of the crystal is the only low energy degree of freedom. But if you have fractional states, actually, it can additionally map to a non-trivial unitary that acts in the space of the degenerate ground states. So this gives you an additional Berry phase contribution. And then that actually changes the quantization condition and it can give you a fractional Chern number.
I see. Yeah, that's basically what I mean by the additional dynamical part. Then,
Exactly, yeah.
how much can one determine, to what extent can one determine this additional U1 part, the additional unitary?
Let's see. For easy cases like Laughlin, we can just write down like U1 and U2 because we know what they should look like. Like it needs to essentially look like the qubit version of the Pauli X and Pauli Z operators. It's an interesting question to ask, and I don't actually know what we might conclude if we had something like Moore-Reed or something that behaves a bit more non-trivially under the action translation. That's something I wanted to think about, but I haven't had the time to sit down and think through. Like it still constrains what U1 and U2 needs to be, but it doesn't uniquely fix it because unlike in the Laughlin case, I think in Moore-Reed, degeneracy is more than just like 1 over like the fitting fraction, right? So there are more degrees of freedom that you need to look at.
Any other questions?
Yeah, maybe I can also make a comment just regarding like the anomaly matching section because I think that is very nice. That's a very nice way to think about this thing. But yeah, like I wanted to just make a comment that like this filling constraint that you have, this beta blah 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 equals nu modulo 1. This constraint a couple of years ago, quite old now, like it was in 2020 or something like that. I also wrote a paper in which I obtained this filling constraint from SPT considerations, basically. So,
Oh, interesting.
yeah. So and the argument is actually quite similar. Like I can see like some.
Yeah, if you can.
Yeah, I can see like a lot of the similar thought was kind of happening here as well. And also, like, the nice thing about like this, SPTs, and then you have this decorated domain wall construction for these SPTs and higher order SPTs. Nice thing is that you can now put in like these crystalline symmetries that you have, especially like there's this kind of so in this old paper by Oshikawa and Run, they argued that there is a generalization of this filling constraint to the case where you have a glide symmetry, right, on your lattice system. They have this.
I see.
They assume that you just divide everything by one half, basically. Yeah, but the idea
Is this
that
the Luran Oshikawa or?
yeah, that's right. Yes.
Yeah.
Yeah, that was a very nice paper. Very, very much like that paper.
Yeah, that's a very nice paper.
Yeah. And the nice thing about the SPT construction is that you can just see that directly. Like you can just see that one half show up when you have glide symmetry, which is, I think it's, I think there's definitely some synergy that can happen with these different approaches to essentially the same problem.
I see. Can you send me the paper afterwards? I would love to take a look.
Of course. Yeah, no problem. And also another question, like potentially off topic, is that there's this thing called like this shift index or something like that. Like that's supposedly
like shift insulators and
yeah.
Like Shang Liu had a paper with Aslam and Ashvin on this.
Exactly.
I think, right?
And also Damson and all those guys. I was wondering how that fits because I still don't really understand the shift index.
Somebody else mentioned this to me and asked me, like, can we also constrain the shift invariant?
Right.
I also don't fully understand what the shift is. That's something, and in general, questions about like, where else can we do this kind of anomaly matching to fix those invariants is something I'm very interested in talking about. So yeah, happy to chat more.
Of course, yeah. Thank you for the very nice talk.
Thank you so much.
Any other questions? I have one more question. So in this talk, if I think very abstractly, this is some interesting interplay between the U1 symmetry and the translation symmetry. And the translation is, of course, modified to magnetic translation. If I think of other symmetries,
Right.
do I have something similar?
So this, I don't know how to think about it in that language, but I can give you one scenario in which a similar anomaly matching happens, which is actually the Skamian story that I decided to skip today. So in the Skamian story, there's like this old work from 90s by Michael Stone that tells you that beta in the Skamian is given by the spin density times the winding number of your Skamian. If you have a single Skamian, it actually feels a Lorentz force as it moves around. And then the size of the Lorentz force is spin density times the winding number. And this has the similar type of constraint actually. So you can say that in UV, you have lattice translations with like one spin per site. So this fixes the spin density in UV from Lipschitz lattice type consideration, right? And this needs to commute. So from that, you can say, oh, the IR one needs to commute too. Minus A2 IR, this needs to commute as well. And then this commutation condition quantizes beta to be a multiple of S, integer multiple of S. So we see that this is S times M being an integer. Here, it's a Skalium configuration, so the configuration itself doesn't have a U1 charge or even like a definite SU2 action. So I'm not exactly sure how to think about this example. And there, sh there should also be an example in like a QED at finite density, like actual field theory, not just like not just oh, like you have a crystal, so it reduces to a single particle problem. There should be some like thing similar happening in finite density QED, because both in the skyrmion case and the magnetic field case, like what's essential is that in the field theory, the translation is actually broken to some discrete things, like a ferromagnet, like nonlinear sigma model for ferromagnet, if you try to quantize it, doesn't have continuous translation. And then the single particle feeding magnetic field on the torus does not have continuous translation. Same thing happens with like finite density QED. There I haven't figured out what the analogous quantized object is actually.
So in this example of skyrmion, there's nothing like the magnetic field. It's just the skyrmion, right?
Right. It's just like a fully spin system. But the Berry phase is, in this case, generated from the motion of the spins themselves, not from external magnetic field.
I do think it kind of makes sense that you weren't able to see the skyrmion contribution from just the translations, right? Because I think there is this classification of skyrmions using pi2 instead of pi1, the fundamental groups.
Right.
So, yeah, maybe there's some other, like, in fact, like maybe higher order things that you can write down, like these algebras of these flux insertion operators or something like that, that you'll be able to probe the actual skyrmions in the system. But that would be a different algebra than the magnetic translations, I think.
Right. And I think at maybe even more basic level, I had two examples, and one of them, the things that tells me how to implement the continuous translation is the Chan number, right? And in the skyrmion example, it's the winding number. It's like a many momentum space object versus the real space object. So the fact that these two appear in a similar setting, seems to me an indication that maybe there's something a bit more universal going on, but I don't know I haven't worked out other examples or found other examples. So it feels a little frustrating. But also exciting.
Yeah, it's very interesting. I also remember a friend of mine who did something similar actually, in which he tried to compute SPT invariance in both momentum space, K-space, and also real space at the same time. Yeah, but
interesting.
Let's just say I'm not sure how much of his work is makes sense, but but yeah, it's definitely a very interesting idea. It's an important question for sure.
So, Thomas, you mentioned for ferromagnet, if I consider the nonlinear signal model of description of a ferromagnet and try to quantize it, there's no continuous translation symmetry.
Right. Yeah, this is a result from Haldane in 80s.
Why is that?
What's the best way to see it?
So just to be sure, when you say the continuous, when you say the nonlinear signal model, you essentially mean the two terms. One is the usual nonlinear signal model. The other is a very ugly Wess-Wheaton for ferromagnet. That term has a coefficient.
Right, like
that term has a coefficient that depends on the size of the unit cell.
Right. There's a berry phase term as right. The ugly term that shows up for the ferromagnet is precisely coming from the berry phase that each spin is feeding, and I think in like 1+. so I can do it in like step by step. I think in 2D, first of all, like before asking if translation exists or not, like we can ask if like does translation commute between the like one direction and another direction. And they don't, and this comes from the fact that there is this like skyrmionic texture, right? The skyrmionic texture gives you a winding number, and then that gives you non-commuting translation. So, okay, that gives you non-commuting but continuous looking translation in 2D. But then I think what you do in like Haldane's argument, and this I don't think I can reproduce in full detail, but what you then say is, okay, now like try thinking about like building a path integral for one-dimensional case. So you have like 1 plus 1D path integral, and then you look at the action of the translation, and like in general, like the translation appears as though it is okay. But in the path integral, you need to like include the instanton configurations in which you have skyrmions in like the 1 plus 1D space. And if you look at the action of the translation of the skyrmion, like something breaks down and then makes it not actually a valid operator that is well defined continuously and gives you like conserved momentum. I think essentially, like even if you started from what looks like a state that has definite like momentum, skyrmion insertion event in the 1 plus 1D that doesn't commute with this momentum and then gets you into a state that has a different momentum.
I see. Also, you also made this comment about how to obtain a unified view of all these phenomena. I think the common feature of all these phenomena appears to be we are talking about something with a spontaneously broken symmetry. Then
Right.
perhaps it will be valuable to think of a parameterized system instead of a single Hamiltonian,
Mm.
and consider something like the high barrier phase.
I see.
So here, this U is precisely what you use to parameterize the symmetry breaking state.
Exactly. And then in the case of skyrmion, we also parameterize the center of mass, and then you look at, in this case, just the normal Berry phase associated with the motion of the skyrmion. So yeah, maybe there's some like other types of anomalies that can be captured if we are, like allowed to introduce, I don't know, more parameters. Maybe we need to have two broken symmetries and then look at the anomaly between them. This I'm just like thinking out loud. Another question is like these both have translation symmetry breaking, and it comes from the fact that often translation gets discretized when you quantize the classical theory, both in the case of a charged particle with a magnetic field on the torus and the skyrmion. And actually, Nati Seiberg has a series of nice papers on this. And one of them is called anomalous continuous translation. And I wonder if there's something similar that could happen to other symmetries, or if translation is like just the most interesting case. So yeah, I think the interesting questions we can keep asking. Like I will keep looking for some generalizations of it. If you have some idea about generalizing it, either let me know or go ahead and solve it, and I'll be very happy to see the results. So either way,
I
I'll be
will
very
think more
excited.
about it. At the moment, I only have something, I don't have anything concrete to say. Yeah, okay. Thank you for the very interesting and insightful talk. See you.
Thank you for having me. Bye bye.